The illusion of state in state space models. Abstract. State space models, SSMs, have emerged as a potential alternative to transformers. One theoretical weakness of transformers is that they cannot express certain kinds of sequential computation and state tracking, which SSMs are explicitly designed to address via their close architectural similarity to recurrent neural networks. But do SSMs truly have an advantage over transformers in expressive power for state tracking? Surprisingly, the answer is no. Our analysis reveals that the expressive power of S4, Mamba, and related SSMs is limited very similarly to transformers within TC0, meaning these SSMs cannot solve simple state tracking problems like permutation composition, and consequently are provably unable to accurately track chess moves with certain notation, evaluate code, or track entities in a long narrative. To supplement our formal analysis, we report experiments showing that S4 and Mamba indeed struggle with state tracking. Thus, despite their recurrent formulation, the state in common SSMs is an illusion. S4, Mamba, and related models have similar expressiveness limitations to non-recurrent models like transformers, which may fundamentally limit their ability to solve real-world state tracking problems. Moreover, we show that only a minimal change allows SSMs to express and learn state tracking, motivating the development of new, more expressive SSM architectures. Figure 1. We prove that SSMs, like transformers, cannot solve inherently sequential problems like permutation composition, S5, which lies at the heart of state tracking problems like tracking chess moves in source target notation, see section 3.2, evaluating Python code, or entity tracking. Thus, SSMs cannot, in general, solve these problems either. 1. Introduction. Recent theoretical work has shown that transformer architecture-based models are incapable of expressing inherently sequential computation. These results reveal a surprising limitation of transformers. They cannot express simple kinds of state tracking problems, such as composing sequences of permutations, which even simple recurrent neural networks, RNNs, can naturally express. In a different line of work, state space model SSM architectures have been introduced as an alternative to transformers, with the goal of achieving RNN-like expressive power for handling problems that are naturally stateful and sequential. But does the seemingly stateful design of SSMs truly enable them to solve sequential and state tracking problems that transformers cannot? If so, this would be a promising property of SSMs because state tracking is at the heart of large language model capabilities, such as tracking entities in a narrative. Heim, 1983, Kim and Schuster, 2023, playing chess under certain notation or evaluating code. This would motivate further research on SSM architectures and their deployment in the next generation of LLMs. In this work, we show that the apparent stateful design of SSMs is an illusion as far as their expressive power is concerned. In contrast to the suggestion by Gu et al., 2021-2022b, and perhaps a broader belief in the community that SSMs have expressive power for state tracking similar to RNNs, we prove theoretically that linear and Mamba-style SSMs, like transformers, cannot express inherently sequential problems, including state tracking problems like composing permutations that RNNs can easily express. Further, our experiments confirm this prediction. Both transformers and these SSMs cannot learn to compose permutations with a fixed number of layers, whereas RNNs can compose permutations with just a single layer. Our results imply that arguments that current SSMs have an advantage over transformers due to being more recurrent or capable of tracking state are misguided. In fact, the SSM architectures we consider are just as theoretically unequipped for state tracking and recurrent computation as transformers are. We first established the theoretical weaknesses of linear SSMs and near generalizations by proving they are in the complexity class L-uniform TC0, which has been previously shown for transformers, them being these SSMs. This implies these SSMs cannot solve inherently sequential problems formally. Problems that are NC superscript 1, including state tracking problems like permutation composition. Permutation composition is a fundamental problem at the heart of many real-world state tracking problems, such as playing chess, evaluating code, or tracking entities in a narrative, implying solutions to these problems, too, cannot be expressed by SSMs, at least in the worst case. At first glance, our results may appear to contradict Gu et al. 2021's claim that linear SSMs can simulate general recurrent models, which can express permutation composition. But the contradiction is resolved by a difference in assumptions. Gu et al. 2021 relied on infinite depth, number of layers, to show that SSMs could simulate RNNs. We, on the other hand, analyze the realistic setting with a bounded number of layers, under which we find that SSMs cannot simulate the recurrent state of an RNN, and in fact suffer from similar limitations as transformers for state tracking. Empirically, we find that S4 Gu et al. 2022a and S6 Gu and Dao 2022 SSMs as well as transformers do not learn to solve the permutation composition state tracking problem with a fixed number of layers, while simple RNNs can do so with just one layer. This provides empirical support for our theoretical separation in expressive power for state tracking between SSMs and true recurrent models. We also find that both transformers and SSMs struggle compared to RNNs on state tracking problems less complex than permutation composition, where it is not known whether they can express a solution. Thus, in practice, SSMs may struggle not just on the hardest state tracking problems like permutation composition, but also on easier variants. Figure 2. Complexity hierarchy within NC1. Transformers can only recognize languages within TC0, Merrill and Sabharwal, 2023a, and we show the same for SSMs, theorems 4.2 and 4.4. Thus, both architectures cannot express the hard state tracking captured by NC1 complete problems like S5, which can be straightforwardly expressed by RNNs. The figure assumes the widely held conjecture TC0 20 equals NC1. Finally, we consider a particular extension of a linear SSM first proposed by Gu et al. 2022c called Liquid S4, Hassani et al. 2023. We show that this extension has sufficient expressive power for state tracking and permutation composition. Empirically, we show that our implementation of this extension learns to solve permutation composition with a single layer, just like an RNN, while being similarly parallelizable to other SSMs. It is an open question whether such SSM architectures with greater expressivity for state tracking are practically viable for large-scale language modeling. 2. Background. We first present the SSM architectures we will analyze. Section 2.1. Our analysis of the state tracking capabilities of SSMs borrows deeply from the circuit complexity and algebraic formal language theory literature. We thus review how circuit complexity can be used to analyze the power of neural networks, Section 2.3, and how state tracking problems can be captured algebraically and analyzed within the circuit complexity framework. Section 3. 2.1. Architecture of state space models. SSMs are a neural network architecture for processing sequences similar in design to RNNs or linear dynamical systems. SSMs have been suggested to have two potential advantages compared to transformers owing to their recur. The illusion of state in state space models, rent formulation, faster inference, and possibly the ability to better express inherently sequential or stateful problems, Gu et al. 2021, 2022b. Several architectural variants of SSMs have been proposed, including S4, Gu et al. 2022a, and Mamba, Gu and Dao 2023. Recently, SSMs have been shown to achieve strong empirical performance compared to transformers in certain settings, particularly those involving a long context, Gu and Dao 2023, Wang et al. 2024. SSMs consist of SSM layers, which can be thought of as simplified RNN layers. We define a generalized linear SSM layer that encapsulates both S4 Gu et al. 2022a and the S6 layer used by Mamba 2023 as special cases. Definition 2.1 Generalized linear SSM layer. Given a sequence 2x1, xn, rk, the recurrent form of a linear SSM layer defines a new sequence of states h1, hnrd, using projections aird and biirdk, which can themselves depend on psi. For each one in, see formula, the convolutional form of the SSM layer defines the same three h1hn computed differently as a summation. See formula. The layer outputs yi equals ci plus dixi n of rk, where ci rk depend on psi. Two common cases of this layer are when ai does not depend on the input, non-gated, section 4.2, and when aii is diagonal, section 4.3. In both of these cases, we will show that the SSM can be simulated in TC0. A generalized linear SSM is made up of multiple such layers, with a linear projection and a nonlinearity applied after every layer. Rush and Karamchetti, 2022. Layer norm can also be applied either before or after the layer. Practical details. In S4 and related SSMs, definition 2.1 is applied element-wise, k equals 1, across all m elements of the previous layer output. Jiu et al., 2022a. In practice, the weight matrix initialization is crucial for training. Our expressivity results, theorems 4.2 and 4.4, apply for any generalized linear SSM, including S4 and S6, independent of initialization. In contrast to S4 and S6, H3 FU et al. 2023 does not meet definition 2.1 because the context is not represented by a single vector. Rather, it resembles a transformer with SSM components. 2.2. Numeric data type. Circuit complexity analysis of neural networks depends to some degree on low-level details about arithmetic and the underlying data type D used in the network's computation graph. We can think of D as parameterized by the number of bits available to represent a number in D. For instance, non-negative integers in left bracket 0, 2 to the power of p, right bracket use p bits, signed integers in left bracket negative 2 to the power of p, 2 to the power of p right bracket use p plus 1 bits, FP16 uses 16 bits, etc. Our main results, theorems 4.2 and 4.4, will go through for any data type D for which the following operations are efficiently parallel computable. For example, in the complexity class L uniform TC0, to be defined shortly in section 2.3. 1. Iterated addition, i.e. summing n numbers in D. 2. Iterated product, i.e. multiplying n numbers in D. 3. Matrix powering, i.e. computing the nth power of a fixed size D times D matrix over D. When D is any finite precision data type, i.e. has a fixed number of bits available, for example 16 or 64, then these operations are easily seen to be L uniform TC0. As Merrill and Sabharwal 2023b argue, however, finite precision data types severely limit the expressivity of neural architectures from a formal perspective. For example, finite precision transformers cannot represent models with floating point weights of parameterized data types that can, approximately, represent any number with a sufficiently large parameter. Interestingly, when D is the data type of n-bit integers, all of the above operations are known to be in L uniform TC0, Hess 2001, Marighetti and Polano 2000. Realistically, however, neural model implementations use floating point numbers with much fewer than n bits. Following Merrill and Sabharwal 2023b, we use the log precision floating point model, i.e. clog n-bit floats, where C is some fixed constant. See Appendix A for a formal definition. Merrill and Sabharwal 2023 showed that iterated addition over log precision floats is in L uniform TC0. We extend the arguments of Hess 2001 and Marighetti and Polano 2000 to show that iterated product and matrix powering over log precision floats are also in L uniform TC0. See Appendix A. 2.3. Limits of transformers via circuit complexity. A line of recent work has used circuit complexity and logic formalism to identify expressivity limitations of transformers on reasoning problems. Angluin et al., 2023, Merrill and Sabharwal, 2023a, Liu et al., 2023, Chiang et al., 2023, Merrill and Sabharwal, 2023b, Hao et al., 2022, see Strobel et al., 2024 for a survey. In particular, Merrill and Sabharwal, 2023, showed transformers can only solve problems in the complexity class TC0, which is the set of problems that can be recognized by constant depth, polynomial-size threshold circuit families. Such circuits, in addition to having standard and, or, and not gates of arbitrary fan-in, can also use threshold gates that output 1 if at least k of the inputs are 1, where k is a parameter of the gate. Informally, TC0 can be thought of as the class of problems that can be solved with extremely parallel, constant depth computation. Problems outside TC0, corresponding to problems that are inherently sequential and thus cannot be parallelized, cannot be solved by transformers. No problems in polynomial time are known unconditionally to be outside TC0, but unless the widely held conjecture that TC0 NC1 is false, many simple NC1 hard problems are outside TC0. In particular, This includes simulating finite automata, NC1 complete, evaluating Boolean formulas, NC1 complete, determining graph connectivity, L complete, and solving linear equations, P complete. These problems have already been shown to be inexpressible by transformers. By showing that SSMs can be simulated in TC0, we will establish that they also cannot be solved by SSMs. 3. State tracking. Informally, a state tracking problem is one where the text specifies some sequence of updates to the state of the world, and the goal of the problem is to determine what the world state is after the updates have been applied in sequence. Capturing this formally requires theory of neural networks can be combined with other insights from algebraic formal language theory to analyze the kinds of state tracking that SSMs can express. In particular, this theory reveals which kinds of state tracking problems are likely not in TC0. This will in turn allow us to find examples of hard state tracking that models like SSMs cannot express. 3.1. State tracking as a monoid word problem. From the perspective of algebraic formal language theory, state tracking over a finite world can be captured as a word problem on a finite monoid. Different updates to the world denote different elements in the monoid, and resolving the final world state after all the updates have been applied is equivalent to computing the product of a sequence of elements, also called a word. Definition 3.1. Word problem. Let M be a finite set and M quarter a finite monoid, i.e. M with identity and associative multiplication. The word problem for M is to reduce sequences in M star under multiplication, that is, send M0, M1, MK to M0, M1, M1, M0, M. Solving the word problem requires reducing sequences of arbitrary length. Example 3.2. Consider the monoid 0, 1, where is addition modulo 2. The word problem is to compute the parity of a string, e.g. 0 bar 1 dar 1. From a state tracking perspective, this monoid captures a world with a single light switch. Identity 0 corresponds to no action, and 1 flips the switch. Modeling state tracking with word problems lets us draw connections between circuit complexity and algebra to understand which word problems are hard to solve. Krohn and Rhodes established that not all word problems are created equal. Some, like example 3.2, are in TC0, while others are NC1 complete, requiring recurrent processing to solve. Because we will show SSMs can be simulated in TC0, it follows that NC1 complete state tracking problems cannot be expressed by SSMs. Whether or not a word problem is NC1 complete depends on the algebraic structure of the underlying monoid. Barrington showed that the word problem of every finite non-solvable group is NC1 complete. That non-solvable groups have NC1 complete word problems is notable because of a documented discrepancy with non-solvable groups not in TC0. The canonical example of an NC1 complete word problem is that of S5, the symmetric group on 5 elements that encodes the permutations of 5 objects. As an immediate instantiation of this, consider a document describing a sequence of transpositions. Swap ball 1 and 3, swap ball 3 and 5, swap ball 4 and 2. Being able to answer the question, where do balls 5 end up, for all possible swap sequences requires solving the S5 word problem. By permutations, Figure 2 shows how many natural state tracking problems, like tracking chess moves, evaluating code, or tracking entities, also encode the structure of S5, meaning these state tracking problems also cannot be expressed by a model in TC0. Rather, in order to solve these problems, the depth of the model would have to be expanded to accommodate longer inputs. Although the S5 word problem is canonical, in this paper we will consider the word problem on a closely related group A5, the alternating group on 5 elements. We do this for simplicity. A5 is a subgroup of S5 containing only even permutations, and is the smallest non-solvable subgroup. We will compare the word problem on A5 to 2 other baseline groups, A4xZ3, a non-abelian but solvable group, and Z60, an abelian group, encoding mod 60 addition. We choose these groups as points of comparison because they all have 60 distinct elements, meaning that the difficulty in learning their word problems will come only from the complexity of learning the group multiplication operation. Page 5 of The Illusion of State in State Space Models. 3.2. Encoding S5 in chess state tracking. Figure 1 already gives some intuition into how state tracking problems encode S5. Out of these examples, the most intricated case is chess. We now give a proper reduction from S5 to tracking chess moves, showing formally that not just S5 but chess state tracking as well is NC1 complete. We define the chess state tracking problem as follows. Input: a chessboard state and sequence of chess moves, where each move is written in UCI notation as a tuple, source square, target square. This differs from the standard SAN notation that represents other information like piece type. Output: the resulting board state after starting in the initial board state and applying the sequence of moves one after another, ignoring draws. If any move is illegal given the previous board state, a null state is returned. We show that S5 can be reduced to chess state tracking, establishing its NC1 completeness, proposition 3.3. S5 can be reduced to chess state tracking in UCI notation via NC0 reductions. Proof: without loss of generality, we consider the variant of S5 where the output is true if and only if the original first element returns to the first position after the given sequence of permutations has been applied. The idea, as illustrated in Figure 1, is to map each element of S5 to a fixed sequence of chess moves that permutes 5 pieces accordingly on the chessboard. Given an instance of the S5 word problem, we will construct an initial board state and a sequence of moves such that the final chessboard state encodes the output of that S5 problem instance. Let M denote the set of chess moves in the UCI, i.e., source square target square, notation. Initial board state. We construct a chessboard similar to Figure 1 but with a black rook at A8 and black queens at B8 to E8. Chess move sequence. We then construct a finite function f from S5 to M star that encodes a permutation pi as a sequence of chess moves. We first factor each permutation pi to a sequence of transpositions. Each transposition tie of T can in turn be expressed as a sequence of chess moves analogously to Figure 1. For example, transposing items 1 and 3 can be expressed as the move sequence A8 A7, A1 B1, C8 C6, B1 A1, A7 C7 A1 B1 C6 E6, B1 A1 C7 C8 A1 B1, which has the crucial property that it transposes A8 with C8. We denote the mapping from translations to chess move sequences as F. Putting it all together, we have C formula. To reduce a sequence of permutations W and S5 star, we let C formula. Putting it all together. We call our oracle for chess state tracking with the constructed initial board state and f of W as the sequence of chess moves. By construction, we can then return true if and only if the rook is at A8. The reduction can be implemented in NC0 because it is a simple element-wise mapping of the input tokens, and decoding from the output chessboard is a finite table lookup. As a fun aside, we note that the chessboard constructed in the above proof is reachable in a standard chess game. The chess sequences encoding permutation sequences are valid in the game of chess, modulo the fact that repeated board states in chess technically lead to a draw. Since S5 is NC1 completed under AC0 reductions, and NC0 is a subset of AC0, we have Corollary 3.4. The chess state tracking problem is NC1 complete under AC0 reductions. Theorem 3.2 of Feng et al. 2023 uses a similar reduction to prove formula evaluation is NC1 complete. Reductions can be constructed for evaluating Python or tracking entities in a dialog as suggested by Figure 1. As for chess, the task formatting for entity tracking affects its hardness. For instance, the formatting used by Kim and Schuster 2023 in their Figure 1 is not NC1 complete, whereas the variant shown in our Figure 1 is. This underscores the value theory for constructing examples of hard state tracking. 4. SSMs can be simulated in TC0. In this section, we show that the convolutional form of many variants of SSM can be simulated in TC0. Assuming the convolutional form of the model computes the same functions as the recurrent forms, this implies such SSMs cannot solve inherently sequential problems, despite their appearance of recurrence and statefulness. We first show containment in TC0 for non-gated SSMs, and then show the same holds for diagonal SSMs. 4.1. Conditions for linear state space models in TC0. Before characterizing specific state space models architectures, we first show that the complexity of computing transition matrix products essentially determines the complexity of simulating in state space model with a circuit family. Lemma 4.1. Let M be a log precision generalized linear state space model. Then there exists a L-uniform TC0 circuit family that computes M's convolutional form if 1. For any integer interval left square bracket j, k right square bracket, the matrix product from j equals 1 to k ai can be computed in L-uniform TC0 as a function of aj, ak to c log n precision for any c greater than 0. 2. For 1 is less than or equal to j is less than or equal to n, aj, bj, cj, and dj can be computed in L-uniform TC0 as a function of xj. Proof. Following the proof structure of Merrill and Sabharwal, 2023a, we describe how to construct a log space bounded Turing machine T sub m that, given x1, xn as input, prints a circuit that simulates M on this input. We first note that for all processing done before or after in state space model layer, projection, nonlinearity, layer norm, etc., T sub m can follow known simulations of such operations for transformers, Merrill and Sabharwal, 2023a, 2024, to output a TC0 circuit simulating this processing. We thus focus on the TC0 simulation of the state space model layer. Recall from definition 2.1 that M's convolutional form requires computing Hj equals summation with limit from I equals 1 to j product from k I plus 1 to j plus 1 akbxj and yi equals chi plus dxj. By the second precondition, T sub m can print a TC0 circuit that computes all matrices involved here. Further, by the first precondition, T sub m can also print a TC0 circuit that computes the inner product in the computation of each hidden state Hj, namely product from k equals I plus 1 to j plus 1 ak. It can now print a TC0 circuit to multiply the resulting product with b and xj, and then print a circuit to compute an iterated sum over the I resulting vectors to compute hj. Cf. iterated addition in Appendix A. It can similarly print a simpler circuit to compute yi. Thus, the entire state space model layer can be simulated by an L-uniform TC0 circuit. We will use Lemma 4.1 to show that any non-gated or diagonal generalized linear state space model can be simulated in TC0. 4.2. Non-gated state space models are in TC0. Theorem 4.2. Non-gated state space model. Let M be a log precision generalized linear state space model such that for any I, AI equals A, BI equals B, CI equals C, DI equals D. Then there exists an L-uniform TC0 circuit family that computes M's convolutional form. Proof. We prove this by showing that both conditions from Lemma 4.1 are satisfied. Computing the matrix product reduces to powering A to the power of K minus J. Crucially, we can use the fact that matrix powering over floats is in L-uniform TC0, Lemma A.8, extending Marighati and Polano, 2000. Finally, A, B, I, C, I, and D, I can be computed in L-uniform TC0 because they are constants. As S4 satisfies the premises of Theorem 4.2, we obtain Corollary 4.3. There exists an L-uniform TC0 circuit family that computes S4's convolutional form. 4.3. Diagonal state space models are in TC0. Theorem 4.4. Diagonal state space model. Let M be a log precision generalized linear state space model where 1 is less than or equal to I is less than or equal to n. 1. The transition matrix AI is diagonal, denoted diag AI, where AI is an element of R to the power of D. 2. Each of AI, BI, CI, and DI can be computed in L-uniform TC0 as a function of x, j. Then there exists an L-uniform TC0 circuit family that computes M's convolutional form. Proof. By the first condition, AI equals product from K equals I diag AI. Iterated multiplication of diagonal matrices is reducible to several iterated scalar multiplications, placing this product in L-uniform TC0, Lemma A5. The second condition from Lemma 4.1 is satisfied by assumption. Thus, M's convolutional form is computable in L-uniform TC0. Since S6 satisfies the premises of Theorem 4.4, we have Corollary 4.5. There exists an L-uniform TC0 circuit family that computes S6's convolutional form used by AMSAB. Proof. For the first condition, note that S6's transition matrix AI is defined as expa BIA for a fixed diagonal A. The set of diagonal matrices is closed under scalar multiplication and matrix exponentiation, so AI is also diagonal. See Appendix B for a proof that the second condition is satisfied by the S6 parameterization. Appendix C extends Theorem 4.4 to hold even when AI are simultaneously diagonalizable rather than just diagonal. Specifically, we prove the following generalization. Theorem 4.6. Simultaneously diagonalizable. Let W be a fixed matrix. Let M be a log precision generalized linear state space model such that, for 1, is less than or equal to I is less than or equal to N. 1. The transition matrix A tilde I is computable to log precision by the expression W diag A hat W to the minus 1, where a hat I is an element of R to the D. 2. Each of a tilde I, B tilde I, C tilde, and D tilde can be computed in L uniform TC0 as a function of Xi. Then there exists an L uniform TC0 circuit family that computes M's convolutional form. This in turn allows us to prove that a simultaneously diagonalizable transition matrix generalization of the S6 layer is also an L uniform TC0 corollary C7. 4.4. Discussion. Theorems 4.2 and 4.4 establish that common SSM variants, like transformers, can only express solutions to problems in the class TC0. This means these SSMs cannot solve NC1 hard problems like evaluating Boolean formulas or graph connectivity. In particular, it shows that they are limited as far as their state tracking capabilities, as they are unable to compose permutations solve the S2-word problem. Corollary 4.7. Assuming TC0 is not equal to NC1, no log precision SSM with the S4 or S6 architecture can solve the word problem for S5 or any other NC1 hard problem. In contrast, RNNs can easily express S5 via standard constructions that encode finite state transitions into an RNN. This shows that SSMs cannot express some kinds of state tracking and recurrence that RNNs can. This tempers the claim from Gu et al. That SSMs have the expressive power to simulate RNNs, which relied on the assumption that SSMs can have infinite depth. In a more realistic setting with a bounded number of layers, our results show SSMs cannot express many state tracking problems, including those which can be solved by fixed-depth RNNs. 5. Extending the expressive power of SSMs. We have shown that S4 and S6, despite their seemingly stateful design, cannot express problems outside TC0, which includes state tracking like S5. We show how SSMs can be extended to close the gap in expressive power with RNNs, allowing them to express S5. Two simple extensions can bring about this increase in expressive power, assuming layer input dimension k to beta 1. First, adding a nonlinearity makes the SSM into an RNN, adding expressive power but degrading parallelism. On the other hand, allowing AIMI to be input dependent makes the SSM more like a weighted finite automaton, adding expressive power while remaining parallelizable. 5.1. Via nonlinearities, one extension to the SSM is to add a nonlinearity, effectively making it an RNN. We call this an RNN SSM layer, HI equals SGN A tilde HI minus 1 plus B tilde XI. A model with this architecture can solve the S5 word problem when the input dimension k is greater than 1. Theorem 5.1. For any regular language L subset sigma star including the word problem for S5, there exists a one-layer log precision RNN SSM with k equals the length of sigma that recognizes L. Proof. The standard constructions for simulating automata with RNNs, see Minsky, 1954, Merrill, 2019 apply. The condition k equals the length of sigma comes from needing to represent token types with linearly independent vectors. Adding a nonlinearity to the output of an SSM layer, as in Mamba, is not the same thing as an RNN SSM. Rather, an RNN SSM applies the nonlinearity at each recurrent update. A downside of this approach is that it becomes nonlinear to parallelize the RNN SSM computation graph with the scan algorithm used by linear SSMs. Blalock, 1990. 5.2. Via input-dependent transition matrices. Another way to get greater expressive power is to let the transition matrix A tilde be fully input-dependent as explored by Liquid S4 Hassani et al. 2023. To illustrate this, we define a minimally different SSM called input-dependent S4 IDS4 that achieves greater expressive power for state tracking. Let pi, a mapping from R to the K to R to the D by D, be some affine transformation where the output vector is interpreted as a D by D matrix, and let A tilde I equals pi xi. Let B C D be fixed C what's I. By definition 2.1, the IDS4 convolutional form computes an iterated product of non-diagonal input-dependent matrices. See formula. In contrast to matrix powers or iterated products of diagonal matrices, iterated products of general matrices cannot be computed in TC0. Mergentini and Polano, 2020. This means that the arguments from theorems 4.2 and 4.4 will not go through for IDS4. In fact, we can show IDS4 gains expressive power beyond TC0. Theorem 5.2. For any regular language L subset sigma star, including the word problem for S5, there exists a one-layer log precision IDS4 SSM with k equals the length of sigma that recognizes L, where sigma is a special beginning of string symbol. Proof. It suffices to show that IDS4 can simulate a deterministic finite automaton DFA. We do this via a transition. Figure 3. Minimum number of layers, lower is better, required to attain greater than 90% validation accuracy on group multiplication problems by sequence length and group. RNN and IDS4 models of constant depth can solve arbitrarily long sequences, while Transformer S4 and Mamba models require diezing monotonically increasing in sequence length. Monoid construction. For any W centrin, let W, QQ be the function mapping a state to its eventual destination state after W is read from that state. For any DFA, this set of functions forms a finite monoid, the transition monoid under composition, following from the Myhill-Nerode theorem, Hopcroft et al., 2001. Further, each monoid element thela W can be represented as a Boolean transition matrix, making matrix multiplication isomorphic to monoid composition. Computing the transition monoid of a DFA allows recognizing valid words. Compute the monoid element for a word by multiplying the elements for its tokens, and then check whether the initial state maps to an accepting state. Fix a DFA and its transition monoid theta. To complete the proof, we show there exists an SSM that, for all W Milanese, computes thela W given input x equals W. Let AI be the transition matrix representation of thela xi. Matrix multiplication is isomorphic to composition of transition monoid elements. We view indices in high as states and define Biak-Dalo as 1 at the initial state Q0 and 0 elsewhere. For other sigma, let Bx6 equals 0. This yields the following convolutional form. See formula. Since x equals w, we conclude that hxxwq0. 5.3 Discussion. Theorems 5.1 and 5.2 show that two minimal extensions of the SSM enable expressive power outside TC0, allowing the model to solve hard state tracking problems. Corollary 5.3. There exists a one-layer log precision RNN SSM and WFA SSM that express the word problem for S5 with a beginning of string symbol, but would these variants of SSMs be feasible to use in practice? Besides expressive power, there are two competing practical concerns that might make these extensions problematic: parallelism and the impact on learning dynamics. Parallelism. To be used effectively in an LLM, a model architecture must be parallelizable on practical hardware. Architectures in TC0 are parallelizable by design, but architectures in NC1 may still be parallelizable to log depth, even if they cannot be parallelized to constant depth. For IDS4, the bottleneck would be computing iterated matrix product with a log depth computation graph. This could be achieved with the scan algorithm similar to S4 and S6. In contrast, it is less clear how to parallelize a model with nonlinearity. Learning dynamics. Another potential concern for IDS4 is that learning dynamics could be degraded. In particular, an iterated product of matrices may lead to vanishing or exploding gradients. However, this is already potentially an issue for the S6 architecture, where the selective gating involves computing an iterated product of scalars. 6. Can SSMs learn permutations in practice? Having established theoretical limitations of SSMs for state tracking, we empirically test how well SSMs can learn such tasks, focusing on the A5 word problem. Since this problem is NC1 complete and Transformers S4 and Mamba can only express functions in TC0, these models should require a depth that grows with the input length to solve this problem. Task. We model word problems, see section 3.1, as a token tagging task. Words are input and input a sequence drawn from one of A5, A4 times Z5 or Z60. At each step I, the label is the product of the first I elements of the sequence. Modeling the problem as a tagging task rather than as a sequence classification task provides the models with more supervision during training, making it as easy as possible to learn the correct function. We tokenize inputs such that each element gets a unique token. Models. We train a transformer as a TC0 baseline, an RNN that we expect can perform state tracking, and 3 SSMs, S4, Mamba, and IDS4, section 5.2. For IDS4, we initialize the affine projection alpha as a random normal centered around the identity, alpha of xi I plus 0 sigma 2. This ensures that at initialization, input-dependent transitions tend to propagate the previous state, which we expect to aid learning efficiency. Experimental setup. We train models on sequences of length n for successively larger values of n and report full sequence accuracy on a test set 0.9. To validate the prediction that SSMs and transformers require growing depth to solve longer A5 word problems, we plot the minimum depth with 90% test accuracy as a function of input sequence length. Results. Figure 3 shows single-layer RNN and IDS4 models learn the word problem for arbitrarily long sequences for all three groups. In contrast, Transformer, S4, and Mamba models require depth monotonically increasing in sequence length to attain good test accuracy for the non-commutative groups. We draw 3 conclusions from this. 1. As expected, S4 and Mamba show the same limitations as Transformers on the A5 word problem. Longer A5 sequences require deeper models, consistent with these models being in TC0. In contrast, RNN's Theorem 5.1 and IDS4 Theorem 5.2 can efficiently solve the A5 word problem. 2. Transformers, S4 and Mamba require greater depth even for A4Z5, which can be theoretically expressed by TC0 circuits. Although Transformer and Mamba models of a given depth perform as good or better on A4Z5 as they on A5, they still require increasingly many layers to handle proportionally longer sequences. There are 2 possible interpretations of this. First, it could be that while these word problems are expressible in TC0, they cannot be expressed by S4, Mamba, or Transformers, which can each likely recognize only a proper subset of TC0. On the other hand, it is possible that these word problems are expressible by Transformers, S4, and Mamba, but that effectively learning a constant depth solution is difficult. 3. Despite this limitation, S4 and Mamba appear empirically better than Transformer at approximate state tracking on the non-commutative tasks. For length n sequences from A4 times Z5 or A5, the Transformer requires at least as many and frequently more layers as S4 or Mamba. Chapter 7. Conclusion. We formally analyzed a family of generalized linear SSMs and showed that, like Transformers, common SSM variants including S4 and Mamba can only express computation within the complexity class L uniform TC0 of highly parallel computations. This means they cannot solve inherently sequential problems like graph connectivity, Boolean formula evaluation, and, of particular interest for state tracking, the permutation composition problem S5. S5 can be naturally expressed by true recurrent models like RNNs and captures the essence of hard state tracking due to its NC1 completeness. In practice, one-layer RNNs can easily learn a task capturing S5, while linear SSMs require depth growing with the sequence length. These results reveal that S4, Mamba, and related SSMs cannot truly track state. Rather, they can only solve simple state tracking problems for which shallow shortcuts exist. On the other hand, we showed that an input-dependent SSM similar to Hassani et al. 2023, Liquid can both express and learn the S5 word problem, providing evidence that the expressiveness limitations of current SSMs can be overcome. Ultimately, this line of work could unlock new neural architectures that balance the parallelism of CART transformers and SSMs with full expressive power for state tracking, enabling LLMs that can benefit from scalable training while having greater capacity to reason about games, code, and language. Chapter 8. Impact Statement. This paper aims to advance the foundational understanding of state space architectures for deep learning. Such work can affect the development and deployment of deep learning models in a variety of ways, which in turn can have societal impacts. However, we find it difficult to meaningfully speculate about or anticipate these downstream impacts here. This concludes the reading of The Illusion of State in State Space Models on Research2U. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.